Alright, this lecture is going to be about deterministic optimization. And this is the first of a couple different lectures that are going to be somewhat of a departure from what we've been talking about in recent lectures. We're going to go from more of a stochastic modeling approach or a discussion of stochastic modeling towards one that's more focused on decision making. So there are obviously two parts of the phrase deterministic optimization. And optimization just means a process of finding the best solution mathematically for a design or a process or a problem. And deterministic means that the system that we're modeling, we're going to make an assumption about that system, which is that there's no uncertainty surrounding any of the model parameters or the processes. That doesn't mean it's not a dynamic system. In other words, it's not an assumption that whatever system or process we're modeling doesn't change through time. But we are going to make an assumption when we're talking about deterministic optimization that if a process or system changes through time, we know exactly how it will change through time. And so that's an important assumption that I think it's worth thinking about as we go through this. And we'll critique that a little more in the next couple lectures. So deterministic optimization centers around finding the values for a set of different decision variables. And we want to find values for these decision variables that optimize some sort of objective, whether that's minimizing cost, maximizing revenues, something like that. So a decision variable could be, for example, how much of different types of products to buy or how much to sell, as well as when to do it. If we're talking about a multi-period system and potentially having prices for different products go up and down, part of the optimization is trying to figure out when exactly to buy or sell. We can also constrain deterministic optimization to reflect actual physical limitations of the system that we're talking about. For example, we might be talking about a factory that produces two different types of products, but it might have a maximum capacity of the number of products of product A, and that it can produce a separate maximum number of products of product B, or number of units of product B that it could produce. So part of my interest in going through what will really just amount to an introduction to this concept is the fact that deterministic optimization is used in a lot of different fields, not just in modeling and making decisions about energy and electric power systems. This is a short list of other fields that use deterministic optimization is shown at the bottom of the screen, but the actual number of fields that employ this approach go well beyond what I've listed. So let's take a look at a concrete example. So let's say there's a supplier that makes some sort of widget or gadget, doesn't matter, and the supplier has a need to meet demand for this whatever it produces, and it has to supply at least 260 units. And it has some options about, or some flexibility at least, about how it does that, because it has two different factories, factory 1 and factory 2. And so we're saying that the collective output of both factories needs to be 260 units. But the cost of producing individual units at each factory is different. So the first equation here, C of x, is the cost associated with operating the factory. as a function of the number of units it's producing. For the first factory, the cost increases as the number of units x increases. And the second factory has a slightly different looking cost function that also increases as a function of y, or the number of units produced. So our objective here happens to be cost minimization. So we want to minimize the cost of meeting demand, producing 260 units. So the objective is to minimize the sum of these two different cost functions. Now, the most trivial way we could answer that is just to say, okay, well, if you really want to minimize c of x plus c of y here, you would just set x and y equal to 0, right? That would result in the lowest possible values. However, we have a constraint on the system. We have to make sure that x plus y equals 260. In other words, we need the cumulative output from both these factories to equal demand. And so we can't just set x and y both equal to 0. We're trying to minimize the sum of c of x plus c of y using some combination of x and y that equals 260. So there are a couple different ways we could approach solving this problem, finding the values of x and y that minimize the cumulative cost function, right, the sum of c of x plus c of y, with the constraint that x plus y has to equal 260. The first is calculus. So some of you may recall that we can use calculus to find minimum and maximum values by taking, in this case, the first and second order derivatives. The downside to doing this, besides the fact that you have to use calculus, is that it can be tough to incorporate constraints, and then obviously the more complicated the problem gets, the more complicated the calculus gets. Another option is searches and or enumeration. And so all this means is looking at every single possible combination of x and y value where x plus y equals 260, calculating the cumulative cost, and then just finding the minimum value. And so here I visualized an example of enumeration. So we have different values of x, different values of y, and then I'm taking on the z-axis, the vertical z-axis here, I'm plotting the value of the cumulative cost function. So I'm adding c of x plus c of y into this combined equation, and I'm looking at different combinations of x and y where x plus y equals 260, and then I'm plotting them. And so in this case, color corresponds directly to value on the z-axis. And remember, we're trying to minimize the cumulative cost of producing 260, and so we want to be as far away from the yellow and as low on the z-axis as possible. And so visually you can sort of see the general zone in which we would find that minimum. It would be some fairly small value of x and fairly small value of y towards the really dark blue section. Now, one issue with searching and enumeration, so going through every single possible combination of our decision variable values to find the minimum, is that if we're going to start looking at more complicated problems, in particular problems that might have lots and lots of different decision variables, not just two, then the space through which we're searching for values of x and y and z and however many decision variables you want to talk about, to look for combinations that give us a minimum is so large that it would take a long time to actually find the answer. So that's a downside to searching. Another option is Lagrangian optimization. Lagrangian optimization is pretty straightforward. So it provides a way to either find the minimum or the maximum of a function. And I'm going to walk you through one example applied to this problem of minimizing the cost of producing 260 units at these two factories. So the general setup is shown at the top. The first step is to create what we call a Lagrangian function, so L of x, y. So the Lagrangian function is a combination of a couple different things. The first is f of x, y, and this is the function that we're trying to minimize. So in our case, that would be the combined cost function for both factories, so c of x plus c of y. And I've written that out at the bottom. So I've added c of x plus c of y, and that gives you 36 plus 1.7x plus 0.04x squared plus 1.8y plus 0.03y squared. That's the combined cost function. And then we have this minus this lambda. I think that's a lambda. And the lambda here is what we call the Lagrange multiplier. And it's sort of a unitless parameter in this case. And then that we're multiplying the Lagrange multiplier times some stuff in brackets. And there's a couple things here. What's in the bracket is sort of the rearranged constraint on our problem. So if we g of x of y equals k is the original form of the constraint, right? So in this case, our constraint is x plus y equals 260. So we have to produce cumulatively at factory 1 and factory 2 260 units. And so we switch this equation around a little bit and set it to 0. So we say g of xy minus k is equal to 0, and that's what we put inside those brackets. So in the case of our constraint, since our original constraint was x plus y is equal to 260, we're bringing the 260 over to the same side of the equation as x plus y, and it takes a minus value, and then setting that whole thing to 0, and that's what goes in the brackets. So we've got our greater Lagrange function here, which is again the combination of the function, the objective function we're trying to minimize, minus the Lagrange multiplier times a rearranged form of our constraint. So the next step here is to take partial derivatives of this entire thing with respect to x, y, and lambda. And when we do that, we get 3 different equations. We can set those to equal to 0, and then we have 3 equations and 3 unknowns. So we want to solve for x, y, and lambda. Ultimately, we want to actually just solve for x and y. But we can, by setting those derivatives to 0 and coming up with a system of equations with 3 unknowns, we can solve for each variable. So let's step through that process. So we're starting out with our the larger Lagrange function. First, we take the partial derivative. So when you're taking the partial derivative of this whole function with respect to x, for example, what that means is you're going through and taking the derivative of each individual term, but anytime you see a y or a lambda, you're just assuming that those are constants. And again, constant values, that is one value, parameters of this equation that don't have x's attached to them, again, are just you're going to be taking the derivative of a constant, and that just equals 0. So, for example, if we're going to take the partial derivative of this whole equation with respect to x, 36 disappears because the derivative of 36 with respect to x is 0. 1.7x turns into 1.7. 0.04x squared, the derivative of that, is 2 times 0.04x, so 0.08x. Anything with a y, we assume to be a constant, that goes to 0. And then the only term left that we have that has an x attached to it comes about when we multiply through the Lagrange multiplier. We multiply it through what's in the bracket. So we have a minus lambda times x, and that just turns into a minus lambda. And we set that whole partial derivative then equal to 0. And we can do the same thing with respect to y, and then also the same thing with respect to lambda. So we get 3 equations where our unknowns are x, y, and lambda. We set them all equal to 0. And so if we want to solve this system of equations, we can rearrange first the value of x and y strictly in terms of lambda. So we're taking those partial derivatives for x with respect to x and y and rearranging those equations so we get x on one side of the equation and everything else on the other side of the equation. So we can define x and y in terms of these numbers, but also lambda, and we can plug those values for x and y into the third equation, which is the third partial derivative with respect to lambda. And when we do that, we can solve for the actual value of lambda. And of course, if we get the value of lambda, then we can plug that back into the partial derivatives for with respect to x and y in order to find those values. And that's just what this illustrates. We're solving for x and y using the value of lambda. That allows us to find the value of lambda. And then we plug that back into the equations for x and y, and we get specific values for x and y here. Just ignore the MW at the end. I told you this was unitless, and it shouldn't say megawatts. It should just be 112 units of x and 147.8 units of y. So those are the values of x and y that minimize this combined cost function. So Lagrangian multiplication or Lagrangian optimization can be a useful approach, but it suffers from a similar drawback as searches and enumeration, and that is that it can be computationally intensive for really big problems. And so we want to look at one more option for solving deterministic optimization, and that is linear programming. So linear programming is a way to find the optimal solution of a problem, whether it's a maximization or minimization problem, using mathematical programming or mathematical optimization. Formally, linear programs are written out like this, where you have an objective function that is you're maximizing the product of a vector c with the transpose taken, where c is just this vector of coefficients, times a vector of x, where all the x's are your different decision variables. It's subject to a bunch of different constraints. So A is a matrix here. You're multiplying it times your vector of decision variables, and you're setting all those up with inequalities. And then you have non-negativity constraints as well. So every decision variable x here, you're saying it has to be greater than or equal to 0, so you can't produce a negative amount of something. So let's unpack this formal structure in a more intuitive way. So the objective function here is c transpose times x, where c is this vector of coefficients and x is this vector of decision variables. So when you're multiplying this vector c transpose times the vector of x, what you end up with is c1, so the first element of c, times x1, the first element of x, plus c2 times x2. And this is the function you're trying to either maximize or minimize. And the way to interpret this is x are the x's are our decision variables. So thinking back to the factory example, x's would be, x1 might be how much to produce at factory 1, and x2 might be how much to produce at factory 2. The coefficients here are could be interpreted here as variable pricing, right? So the cost per unit of producing something at factory 1 and the cost of producing something at factory 2. So we want to minimize this total function. The second part of this are the problem constraints. And so we are multiplying a matrix A of coefficients times our vector x of decision variables. And when you do that, using matrix multiplication, you end up with a system of equations. And here B is also a vector as well. So you say the matrix A times the vector x gives you linear combinations of every value of x in terms of their relationship to the different coefficients specified in the matrix A. So you have the first element of the matrix A times x1, and so the two subscripts for the A's mean row and column, basically. So you have first row, first column A times x1 plus first row, second column A times x2 is less than or equal to the first element of B, the vector B, and so forth and so on. And so what this is basically doing is constraining the values of x1 and x2 here. And then we have non-negativity constraints at the very bottom, and all that's saying is that every value or every element of our vector x, all our decision variables, have to be greater than or equal to 0, so we can't produce a negative amount. So let's walk through just a simple example of how we would set up a problem like this. So we're not going to solve this one, but I just want to get you in the frame of mind of sort of taking a word problem like this and putting it into the structure of a linear program. So let's say we have a farmer, and the farmer has a piece of land that has an area of L. So L is, we're going to measure here in square kilometers. And the farmer has a choice to make. He has to plant some of that with wheat, some of that with barley, some combination of the two, or all wheat and all barley. Those are his two choices about what he can plant on every square kilometer of land that he owns is wheat and barley. He also has a limited amount of fertilizer, so he has a certain amount, F kilograms of fertilizer, and he has a limited amount of insecticide in P kilograms. And we know that every square kilometer of wheat that he plants, he's going to require a certain amount of fertilizer, F1, and a certain amount of insecticide, P1. And for every square kilometer of barley he plants, he's going to require F2 kilograms of fertilizer and P2 kilograms of insecticide. So all that is to say that 1 square kilometer of wheat requires a different amount of fertilizer and a different amount of insecticide than 1 square kilometer of barley. So each of the products that you can sell here also has a separate price. So S1 is the selling price of wheat per square kilometer, and S2 is the selling price of barley. So our decision variables in this case are X1 and X2, and those are the area in square kilometers that are going to be planted with wheat and barley. So we could conceivably each one could take the value 0, right? So we could plant all wheat, and then the value of x2 would be 0. Or we could plant all barley, and so the value of x1 would be 0. Or they could both be positive, right? But neither one can be negative. And so the way we express this problem in sort of standard linear programming form is to first identify what the objective function is. And so we're trying to, in this case, maximize revenue. We're not really worried about costs here. We're just maximizing the value of the land. And so we're trying to maximize the sum of x1, which is the amount of square kilometers of wheat we produce, times the selling price of wheat, plus the x2, which is the area of barley that we plant, times the selling price of barley. So S1 times X1 plus S2 times X2. We are trying to find the values of X1 and X2 that maximize that function. But we have a lot of constraints here. The first one is we have a limited amount of land, right? We know that the total area of the land that we can plant is L, which means that the sum of X1 and sum of X2 has to be less than or equal to L. We also have a limitation on the amount of fertilizer that we have. And so we've said that the amount of fertilizer required for a square kilometer of wheat and barley are different. And we specified that in terms of the F1 and F2. So F1 is kilograms of fertilizer per square kilometer, and F2 is the same units, right? So kilograms of fertilizer per square kilometer. And so we can define the total amount of fertilizer used for wheat as F1 times X1. And the total amount of fertilizer used on barley is F2 times X2. And so the sum of those two terms we know has to be less than or equal to the total amount of fertilizer we have, which is F. And we could do something similar for insecticide. And then we also have non-negativity constraints again. So X1 could be 0, X2 could be 0. They can't both be 0 because that wouldn't maximize our revenues. But they definitely cannot be negative. So now that we have set up a problem, how do you solve it? And there's a number of different approaches for solving linear programs. And they're all basically algorithms. And so we're not going to solve one by hand, although that's a useful exercise. And what I'd like you to do is watch some of these videos that does walk you through how these problems are solved. And I think it's very intuitive to go through and watch these to get an understanding for how the underlying algorithms in linear programming solvers work. But we would never do this by hand. Most statistical and mathematical programming packages include solvers that use these algorithms to find solutions. And so if you put linear programs into MATLAB or something else in the predefined structure, then there's a solver already built into MATLAB that will find the solution for you. So let's go back to the original factory example here. So we used a couple of different optimization approaches to solve this problem. If we're trying to meet a demand of 260 units here, we have two different factories that have two different cost functions. We want to figure out the value of x and the value of y that minimizes the sum of these two cost functions, with the constraint being that x plus y has to equal 260. And the question here is, can we use linear programming to do this? Can we put this problem in a structure like the one we just saw with the farmer? So here's the first clue to answering that question. If we visualize or plot out the cost functions for each of these factories, what we see is that they are non-linear, right? So the cost associated with producing a certain number of units at each factory increases as a function of the number of units produced at each factory, obviously, but it increases in a non-linear way. And if we look at the combined cost function, so if we add c of x plus c of y, and we explore the different values of that function at different values of x and y that adhere to the constraint that x plus y is equal to 260, we clearly get something that's nonlinear in this case, right? So this is the combined cost function where on the y-axis here you have values of c of x, y, and on the x-axis here you have different values of x, but you could view that equally as something that implies a value of y, since we know that x equals 260 minus y because of our constraint here. So the upshot here is that the cost function is nonlinear. So if we have a nonlinear cost function, that means that we can't put it into a linear program, and so we have to figure out a way to make the cost function linear. And one option for doing that, the least sophisticated option, is to come up with a linear approximation of each cost function for each individual factory. And so that means basically using linear regression to model what we know is a nonlinear cost function. So that's what's illustrated in this top figure. We're just fitting the line of best fit to this nonlinear function. And so what we're more or less assuming by doing this is a constant marginal cost. Now, just by eyeballing the cost function and then at the bottom the marginal cost function, which is the derivative of the cost function, it's pretty clear that the marginal cost increases. And what that means is that increasing, adding one additional unit of production at factory 1, each time you increase the level of production, that the added cost of producing one more increases, right? And so by coming up with a linear approximation of that cost function, we're basically assuming that the marginal cost is constant and that it's 11 in this case. And we can do the same thing for factory 2 as well. And so what we're really doing here is we're taking this original cost function for factory 1 and we're saying, all right, we know this is imperfect, but we can approximate this function by just using a line. So we're basically saying that we're going to say c of x goes from 20 plus 1.7x plus 0.04x squared, and we're going to say now we're just going to model that same cost function from factory 1 as 11x. And we're going to do the same thing for factory 2. We're going to say that the cost function is no longer c of y equals 16 plus 1.8y plus 0.03y squared. We're going to just say it's 9y, and that second equation should say 9y, not 9x. But in both cases, this is a pretty poor assumption. Just visually, I think on the previous slides you can see that it doesn't do a great job of approximating the actual shape of the cost functions, and the end result is that we get a fundamentally different answer to the problem. So remember, our objective here is to minimize the cost of producing a cumulative amount of 260 units from the two factories. And we haven't really talked about putting any constraints on the maximum capacity of either factory here, so we're going to assume that you can produce as much as you want. And we saw that the original answer was producing 147 at 1 and 114 at 2 or something like that, or maybe I have those backwards. But we're definitely going to produce some of each at each factory. But if we use linear approximation on each of the cost functions, so we're modeling the cost of producing at factory 1 as 11x, and the cost of producing at factory 2 as 9y, then it's clear that to minimize the cost of producing 260 units, we would just produce everything at factory 2, because it costs us 9 dollars or cents or whatever to produce each unit, as opposed to $11 or cents at factory 1. And so we got a fundamentally different answer here that's not representative of reality. So a much better strategy when it comes to converting a nonlinear cost function into something that's linear so that it can be incorporated into a linear program is piecewise linearization. So we're taking some sort of nonlinear cost curve and we're breaking it up into different intervals, and each individual interval we will represent through some sort of linear approximation. And the more intervals, discrete intervals that we model, the better the fit is for each individual linear approximation. So you can sort of imagine that if we're breaking this line up into increments, as the number of increments that we're breaking it up into approaches infinity, then we're just reproducing the curve here, right? So you have to make some decision about how many different increments you want to break it up into, and often that decision is sort of made for you by computational limits. So if we broke this line up into 1,000 different intervals, we would have a lot of different decision variables, and so that could be more computationally complex. And so the basic strategy here is converting a nonlinear cost function into one that is linear. And in this case, our decision variables are x1, x2, and x3. And each one of those is basically telling us, x1 describes the number of the level of production between 0 and D1, and x2 describes the level of production between D1 and D2 on the x-axis, and x3 describes the level of production between D2 and D3. And so what you can tell is the slope of each of these lines, of the linear approximations in each interval, is increasing, right? So it costs you less to produce between 0 and D1, it costs you more to produce between D1 and D2, and it costs you even more than that to produce between D2 and D3. And so if you're trying to minimize the cost of producing a certain number of units here, you would automatically start by producing some value of x. And once you get up to the value of x, x1, the maximum value of x1, which is d1, then you start producing some value of x2, and then the total amount of x2 you can produce is d2 minus d1, and then you start producing in the x3 range. And we have a number of constraints on the system here. And the first is that the total amount that we produce has to equal x1 plus x2 plus x3. The total amount of x1 we can produce has to be less than d1. Total amount of x2 we produce has to be less than d2 minus d1. Total amount of x3 we produce has to be less than or equal to d3 minus d2. And the objective function here is really just the total amount that we produce in each category, x1, x2, and x3, times the cost of producing, the marginal cost basically of producing each unit in there. And so that's the slope of each line. And the slope of each line we're calculating for each individual interval here as the difference in y value between at each interval boundary divided by the length of that boundary. So again, in the objective function, the coefficients in front of x1, x2, and x3 are just the slopes of the different parts of the objective function that we've broken up into linear approximations. Now, why this works is because if we're trying to minimize the cost here, it works because x1, we'll always exhaust the amount of x1 we can produce before we start producing x2, and that's because we have because of the particular shape of the cost function here, x1 is always more expensive to produce than x2, or at least less expensive to produce than x2, and x2 is less expensive to produce than x3. Now, if we were going to maximize this same function, it won't work, because the linear program would want to start by producing x3, the most expensive unit, and so in this case, we can only come up with a linear approximation here. I mean, there are other ways of coming up with a linear approximation if you wanted to maximize the function. It's just more complicated. In this case, we don't need any sophisticated constraints because it's a minimization problem. So there's another class of linear programming. So so far we've talked about linear programs in which the decision variables are continuous, right? So we could produce any possible value of x and y. But there are, as you can imagine, a number of problems where we would need to represent certain decision variables as either integers, so you can only produce integer values of, number of units at a factory or something else like that, instead of continuous variables. And we might need situations in which part of the problem is determining whether to turn something on or off. And so in that case, we might need binary variables. And so these would be decision variables that can only take the values of 0, 1, with 1 indicating on and 0 indicating off. So let's go through an example of how we would set up a binary or integer only program. So let's say a city sewer utility or water utility has to decide what capital investment projects they're going to pursue in order to minimize long-term operation and maintenance costs. And they have a couple different decision variables. And each decision variable corresponds to a specific project that they could possibly undertake. And in this case, we have 4 different ones. They could do sewer rehabilitation, wastewater treatment plant rehabilitation, a sewer rebuild, and a sewer rehab. So those are decision variables x1, x2, x3, and x4. And in this case, the possible values that all of those x's could take are 0 and 1. Those are the only 2 values that we can assign to x1, x2, x3, and x4. We have net present value associated with each project, and then the capital requirements for each project. So the net present value sort of includes cost, right? So it's discounted costs minus revenues or revenues minus costs, over time. And so all of these are positive, which suggests that there is any one of these would be a good financial investment, right? So we're not really thinking about which one's going to be a better financial investment or not. However, we do have a constraint on our system, right? And that is that we only have $25 million. And we're trying to figure out a way to maximize net present value by making a decision about each one of these infrastructure projects, given the constraint that we only have $25 million up front to invest. And each one of these projects has a different capital requirement associated with it. So we want to figure out how to spend that capital in the way that maximizes net present value. And our decision variables here are going to be putting a 1 or a 0 for each value of x shown here. So our objective function here is to maximize the sum of x1 plus x2 plus x3 plus x4 times the associated net present value for each one. So the net present value of decision variable 1, the sewer rehab, is 70. So we have 70 times x1 plus 50 times x2, because the net present value of decision variable 2 is 50, and so forth and so on. Now, our constraints here, the first one is that we have a limited amount of capital here. So whatever values of x we assign, whether it's a 1 or a 0 for each case, that activates the capital requirements for each project. And so what we're saying is that the total amount of capital required for each project is a function of the capital requirements for each project times whether or not we pursue it or not, which is the value of 0, 1 that we place in x. So to form the capital constraint here, we have 20 times x1 because the capital requirements of project 1 are $20 million. But that goes to 0 if we don't pursue it. And the way we signal not pursuing that is if we say x1 is equal to 0, because then we would have 20 times 0 is just 0. But we add all these up, and we say that the total amount of capital has to be less than $25 million. And then we have constraints on the variables themselves. We're saying that each of these are binary variables. So, a big reason why we're going to go through some deterministic optimization in this class is because that is and more specifically, mixed integer programming. So this is types of linear programs that have some variables that are continuous variables and some that are binary. This is the main way that electric utilities schedule production at power plants, electricity production at power plants, in order to meet electricity demand. And this is a special, there's a special class of mixed integer linear programs called unit commitment models that help utilities do this, and everyone uses this approach. Academics use it, researchers, industry, etc. And you can make these models, more or less sophisticated depending on what your objectives are. But it's a really good class of models to sort of understand. And so the primary use of binary variables in unit commitment models is to turn power plants on and off. And then we use continuous variables to model how power plants, how much electricity they produce once they're turned on. And so that's what this figure at the bottom is supposed to show. Most power plants have some sort of minimum generation requirement. So they don't actually go down to producing 0. So there's some decision that's made to turn them on, and then they're producing a minimum amount of electricity. And then once they're online, the utility has to decide how much exactly they're going to produce, and they can ramp that production up until their maximum capacity. Okay, we're going to go into much more detail next time about mixed integer linear programs applied to unit commitment problems, so scheduling generation at power plants. I listed one reference here who's a colleague at UC Davis who teaches a deterministic optimization and design class for engineers, and it's a really good resource. So I think if you Google this, you could, I think it's like his sort of semester's worth of notes for his class. So a really valuable resource to take a look at if you're curious about learning more about this stuff.